We have a few more examples to look at, and then we're also going to talk about some properties of definite integrals. So here I have this function that I've drawn. This is the function f of x, and under each region, here I have an area of 4 between a and b. Here I have an area of 5. Here I have an area of 1. So I'm telling you the area of each of those shaded regions. I want to use the graph here along with the area of these shaded regions to evaluate the definite integrals. So here I have first up the integral from a to b of f of x dx. So starting at a, moving towards b, remember this is the definite integral. It tells us the net area. So that net area I'm going to say is, well, it's just 4. I told you the area, so we just need to identify and recognize that this represents that area. So we just need to interpret that essentially as our area. Next, I've got the definite integral from b to c of f of x. So starting at b, working our way over to c, what is the net area bounded by our function? So here our area is 5. But remember that this definite integral over here, this guy represents net area. And when we talk about net area, we count that area that falls below the x-axis is negative. So we're not just simply going to say that it's 5 because this blue shaded area is below the x-axis. We're going to say in this case that it is negative 5. So we want to make sure that we include that negative sign for any regions that fall below the x-axis. So this blue shaded region that falls below the x-axis, we want to make sure we're counting that as negative. Next, I've got the definite integral from b to d. So this one's a little bit different. So I want to start, actually let's highlight it. We're going to start right here at b, and we're going to integrate over to d, and I would like to know, well, what is the net area of our function over that interval? So here I have actually two different areas. I've got this blue shaded area of 5, and I've got this green shaded area of 1. The blue area falls below the x-axis, the green area falls above the x-axis. And keeping in mind, again, I'm thinking about net area. I'll just take this area that falls below the x-axis, I'll make it negative, so negative 5, and then add on the area that is above the x-axis, so adding 1, negative 5 plus 1. In this case, my net area would be negative 4, so this definite integral is equal to negative 4. And then finally, the definite integral from a to d. So this time I'm saying, okay, starting over here at a, working our way over to d right here, what is the net area? So again, I'm just counting area above the x-axis is positive, area below the x-axis is negative. So we have the red area of 4, that's above the x-axis, so that's positive, plus negative 5, that blue area falls below the x-axis, so that's negative. I'm going to say plus negative 5, but you could also, of course, say minus 5. And then we have that small area of 1 there, that's above the x-axis, so 4 plus negative 5 plus 1, that would give me 0. So this is kind of interesting. What this definite integral is telling me is that the net area is 0. That means that the area below the x-axis is exactly equal to the area above the x-axis. So that's kind of an interesting little detail of this definite integral. Finally, we have some integration properties that we should talk about here. So first, the definite integral from a to a of f of x dx, this is equal to 0. And I want to talk about why this one is here. if we go from a to a, if my lower limit of integration is the same as my upper limit of integration. Even if I go back to this example and kind of draw this in, if I want to go, let's say I'm talking about a different point. Let's say I'm talking about, how about this point right here? Let's call this point, how about E? If I want to integrate from e to e of f of x dx, I'm saying what's the area of this purple line that I've drawn in there? Well, area needs to have width, right? You would say, okay, what's the width of this shape? But since we're not moving to the left or to the right, it has no width. And if it has no width, it has no area. So the definite integral in that case is 0. So if your lower limit of integration is the same as your upper limit of integration, it doesn't matter what your function looks like. That definite integral is always going to be 0 every single time. Next up, we have the definite integral from a to b of f of x dx. If I wanted to change the limits of integration, if I wanted to take these two and swap them, so now my new lower limit of integration is b, my new upper limit of integration is a. What happens is that integral will change sign. It still has the same numerical value, it's just the opposite sign. So that means if I wanted to look at, let's say, the definite integral from 1 to 3 of f of x dx, if I said that was, I don't know, how about we say that's 5? If I wanted to integrate then from 3 to 1 of f of x dx, that's equal to -5 in that case. 3 and 4 we've seen a little bit of for indefinite integrals. So here this says in number 3, if I have a definite integral of a sum or difference of two functions, I can take that definite integral and sort of distribute it to each one separately. So I can look at the definite integral of f of x dx plus or minus the definite integral of g of x dx. I'm not changing the limits of integration or anything. I'm just splitting this up into two separate definite integrals. And that only will work if you're adding or subtracting these two functions. If you're multiplying and dividing, well, we're going to have to talk about that still. Similarly for 4, here I have a constant multiple of c. You can take that constant multiple of c and you can factor that to the front of your integral. So rather than multiply first and then integrate, we can actually integrate and then multiply by our constant c. So we can factor out a constant multiple. 5, this one is kind of interesting here. It says if you want to integrate from a to b of f of x dx, that's the same as the integral from a to p of f of x dx plus the integral from p to b of f of x dx. And the way I think about this is you sort of just have a midpoint here, like a halfway point. So if I go back and look at this example up here, let's take this part C right here. Here in part C, when we integrated from b to d, what we really did, we kind of did this without even thinking, we said, okay, that's the same as integrating from, and so if I want to start at b, end up at d, I can put a halfway point right there at c. I can integrate this function from b to c of f of x dx plus the integral from c to d of f of x dx. And then we said, okay, what's the net area right here between b and c? Well, that was -5 plus, and then, all right, what's the net area between c and d? That was 1. Oops, that was 1. Adding those together is how we came up with -4. So you can sort of add in a halfway point. If I want to go all the way from b to d, I can go first from b to c and then c to d and get the same exact answer. The last one here is a little bit wordier. It says the function absolute value of f is integrable on the closed interval a to b, And the definite integral from a to b of absolute value of f of x dx is the sum of all the areas of the region bounded by the graph of f and the x-axis. So notice we're saying the sum of all the areas of the regions. Doesn't matter if it's above the x-axis, doesn't matter if it's below the x-axis. Here you can think about this as total area. So now we're just counting all area is positive. It doesn't matter whether that area falls above the x-axis or below the x-axis. So when we're working with absolute value of f, we're really looking at, you can look at just the graph of f. So you can just look at the graph of regular f and just sum all of those areas together, regardless of whether it falls above or below the x-axis. So here, to finish this section up, we're going to look at just one last quick example here using these integral properties. Assume here that the integral from 1 to 4 of f of x dx is equal to 8, and the integral from 1 to 6 of f of x dx is equal to 5. We're going to evaluate these integrals. So first I have the definite integral from 1 to 4 of 5 times f of x dx. So I have no idea what f of x looks like, but I'm given this information about the definite integral over a couple of different intervals. So first I see, okay, this 5 right here, that's a constant multiple. I probably want to factor that out front. So this really says 5 times the definite integral from 1 to 4 of f of x dx. And then I can say, hey, this piece right here, the definite integral from 1 to 4, that's just equal to 8. So I really have 5 times 8, which would give me 40. Very cool. All right. What about the definite integral from 1 to 1 of f of x dx? Notice I don't have any information about the definite integral from 1 to 1. But I do stop and I say, hey, my lower limit of integration is exactly the same as my upper limit of integration. Which means I don't need any information. I don't need to know anything about f of x, because I know that if my lower limit of integration is equal to my upper limit of integration, that definite integral will always be 0. Part C, here I have the definite integral from 4 to 6 of f of x dx, and this one's a little bit tricky here, because I don't have from 4 to 6. I only have 1 to 4 and 1 to 6. So I would break this apart a little bit. I would say, okay, let's start with the biggest definite integral. If I wanted to integrate from 1 to 6 of f of x dx, we said you can kind of break that up. You can go instead from 1 to 4 of f of x dx plus the definite integral from 4 to 6 of f of x dx. I know what these two values are. Those two values are 8 and 5. So I can just now take those two numbers and plug them in. So I have, let's see, definite integral from 1 to 6. We said that was 5 is equal to definite integral from 1 to 4 of f of x. We said that was 8 plus, I don't know what this integral is. I'm sort of treating this almost like my variable here. I can just solve this equation algebraically. If I subtract 8 from each side, I should end up with negative 3 is equal to the definite integral from 4 to 6 of f of x dx. One last example here then, I have the definite integral from 6 to 1 of f of x dx. Well, how is that different from the definite integral from 1 to 6? I've switched the limits of integration, right? Look at my limits of integration down here. Here my lower limit of integration is 6, but what's given to me is the upper limit of integration is 6. So that means I'm going to have the same numerical value. It's still going to be 5, so this is still equal to 5, But because I've switched the limits of integration, I have to switch the sign. So now it is a -5 rather than a +5. So right now, the big takeaway from this section is that the definite integral tells us the net area under the curve. And right now, we don't have a lot of great ways to find that net area unless we're dealing with geometry or unless it's given to us in some way. In the next section, we're going to see, hey, is there a way that we can use what we know so far about our functions, about calculus, about, say, perhaps indefinite integrals? How can we put all of that together and actually find the net area under the curve a little bit easier?